Testing, testing, 1, 2, 3, testing. Testing, testing, 1, 2, 3, testing. Testing, 1, 2, 3, testing. Testing, testing, 1, 2, 3, testing. Audio is very weak. Testing. Sonido, 1, 2, 3, ah. Audio is very weak. Testing, 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 testing. 1, 2, 3. Sonido, 1, 2, 3. 1, 2, 3. I really don't know where it's supposed to come up. Testing, testing, testing. 1, 2, 3. 1, 2, 3. 1, 2, 3. I really don't know where it's supposed to come up. Testing, testing. Hello, everyone, and welcome. My name is Evie, and I would like to show you this. 1, 2, 3. Hello, everyone, and welcome. My name is Evie, and I would like to show you this. 1, 2, 3. Dang. Hello, everyone, and welcome. My name is Evie, and I would like to show you this. 1, 2, 3. Why are you so low? So low. Uh, why are you so low? So low. Why are you so low? Hee ha hoo ha. Hee ha hoo ha. Is that because my headphones is low? Hee ha hoo ha. I just turned up my headphones. Does this make it better? My headphones is low? I just turned up my headphones. Does this make it better? My headphones is low? I just turned up my headphones. Does this make it better? My headphones is low? I just turned up my headphones. Does this make it better? My headphones is low? Oh, yo, is this completely live? Oh, man. Okay, I was just trying to test this out. All right, we're live, I guess. Oh, yo, is this completely live? Okay, let me turn this off. I don't want to. I was just trying to test this out. How do I stop testing? We're live, I guess. No, we're not studying for the GRE right now. We are. Okay, so we're just jumping right into it. Welcome. So today I'm actually going to cover a pretty interesting concept. I want to discuss why the heck did my football coach make me gain weight? So I played football. It's a contact sport. You're bumping into each other. What I did here is do a bunch of math nobody wants to hear about. I'll probably make a separate video on that. But the idea is what happens if you have a ball or some type of mass that collides together and they basically bounce off each other. And what happens if one's standing still and one kind of goes full blast at it? You could think of me standing still, somebody runs right into me, poof, and blasts me out of the way. What happens? So if we could assume completely elastic collision, which isn't necessarily the case with soft bodies like ourselves, I'm not gonna say I'm too soft to myself, but I probably am right now, but not back then. Um, I'll just jump to the answers. What the equations tell me is that if we actually weigh the same, one mass kind of gets blasted out of the way, and the one that was doing the blasting stands still. And if this mass that's moving is bigger, it'll keep moving forward. And that's what you want in football. You want to move forward and basically not let someone move forward, or if you're running the ball, you move forward and fall forward. And if you're smaller, you're gonna bounce back while the other one still moves forward. So no matter what, you're transferring energy to the other ways. I want to show some videos that demonstrate this. So in this case, we actually have these metal balls in this what's known as Newton's cradle. So they're actually going to bounce back and forth. What you can see happening here is one ball's hitting it, and notice how like all the energy is going. This one stays stopped. This one's moving forward. It moves along in the chain, so it's a little bit more difficult to see. But look, this is another great example from the slow mo guys. This ball is filled with water. It's about the same size and mass as this guy's head. Look what happens. So this thing's moving. This guy's head still. What's gonna happen? Boom! His face gets blasted. Notice the ball. What happened? We're gonna rewind it back a little bit. The ball was moving. It stays still. This guy's head moves forward. It looks like it moves back a little bit, but that kind of shows that hey, this had similar mass. We'll see it again. Super cool. Shout out to the slow mo guys. And so here's an example of a ball. So there's no water in this one. This is actually by the slow mo guys as well with James Corbin. This ball's light. So based off the equations, it should go bounce back. And this guy's still gonna move forward. That's exactly what we see. His head moves a little bit that way, the ball bounced back. Boom. Head forward, ball back. Because the ball's way lighter. So here's an example. It's a little bit tougher to see, but you can see this golf club. It's moving at a certain speed, okay? And notice it gets slowed up, but it continues moving forward. Boom. That's very difficult to see. I don't know. Let's see if we can try to find a better spot. It's so difficult to see. But if you look carefully, we could notice that the golf club, actually reduces its speed slightly. No, the golf club. Sorry, it slowed up and the ball kept moving forward. There's a lot of mass behind this, and that's why it keeps moving forward. If we had something that was only a little bit heavier, we'd be able to see this. And so, kind of playing around with the equations, we'd actually be able to plug these in and see how basically what's going to happen. What's interesting is if we take these equations to the limits. So what I did in these equations, or I basically wrote down. So this is the equation that's going to happen just purely based off the mass difference. So when they're equal, it's zero. So that means the final velocity of the first one is zero. This one keeps moving forward. And um, if the second mass, so like we'll kind of go back to our picture right here. If this second mass is huge, like I basically said, it's like, say think of it as the size of the Earth. If you throw a bouncing ball at the Earth, what happens? The Earth does not move, but the bouncing ball is gonna bounce back with the same velocity. Interesting, right? So this thing's going, say, 10 miles an hour. It's gonna bounce off this, and like it's barely gonna move. It's huge. So now let's look at it in the other way. What if this thing's like the Earth and it's gonna hit a bouncing ball? Bouncing ball still, and the Earth is gonna keep moving, and the bouncing ball is gonna like move as well. What we end up finding, and I thought this was really interesting, is that it's two times whatever speed the big mass was going. So in this case, if say you have Earth, something massive, or a golf club you could think of that's huge compared to a little ball. If it hits it, if this the golf club swinging at like 100 miles an hour, if it's super super big, this thing's gonna go flying 200 miles an hour, right? I don't know how fast golf balls really go, but I thought this was so cool in terms of the equations. This might look like Chinese or some other foreign language you don't understand, but the equations speak to those who know how to understand them. And all of this we just pulled from some basic physics equations of momentum and energy. I thought this is pretty neat. And so, kind of to answer the question, why is it that coaches, specifically football coaches, American football coaches, why do they want you to put on mass? So when you hit somebody, you fall forward and you don't get knocked back like this ball. this example, right? If you're a little guy trying to tackle somebody, boom, you're gonna bounce right off them, right? And if you're the same weight, you can at least completely displace them. And so that's why they want you to be the same size. There's a lot of different neat examples of this. This is just to scratch the surface. Another neat example is kind of a quiz that we can go into. All right. Um, what I remember being asked. So this is what really sparked my interest and got me super excited about math. So or physics, right? Um, here, this if say you're running a bunch of experiments and you have neutrons flying. So they're neutral particles, neutrons. If you had the choice between choosing a lead wall, so you could think of this as almost bulletproof. It's huge, this massive steel wall. You could hide behind a lead wall. You could hide behind maybe let's just say concrete, or you could hide behind some type of like plastic jelly where so this is going to be some type of plastic or some type of water container. Which one would you choose to hide behind? These neutrons are coming at you and will do serious damage. What would you hide behind? You know, the lead's massive. It weighs a lot. It's super thick and dense. Um, concrete, we all know how it feels to get land on concrete. Plastic, it can be soft sometimes. It could be a little hard. And water. I remember contemplating this, and in physics, people were saying all these different things. I was like, man, what's going on? Somebody said beeswax. Like they use beeswax to hide behind. The professor's like, yeah, and I was like, what? I mean, these people obviously knew what the heck they were talking about, and he named off beeswax. So these were the solutions: beeswax, plastic, water. Why would anyone hide behind those if you have neutrons flying at you? Could you think? Well, one might guess, it took me a while. I remember sitting there thinking, man, what's going on here? And then it hit me. What were we just discussing? We're talking about balls flying, right? What's similar mass to neutrons? Hydrogen, protons, right? Which one has the most amount of protons? Well, water, H2O, it's literally protons with oxygen, right? And then beeswax, it's a carbon form. If you take an organic chemistry, you know that this has H's on it. Same thing with plastics. This is a carbon form that has hydrogens on it. And what's so special about these? So if this hits these massive big balls, these neutrons are going to bounce right off. Great. You think you'd be protected, right? Maybe not. What could happen with this? This could bounce off one of these metal balls, bounce back, and it'll just basically ping pong until it goes through. Some of them will go back, but they'll go through. Maybe same thing with concrete. It will go forward, backwards, da da da. Some will go through and blast you. Now you're dead. We don't want that. But with these hydroforms, what could happen if these neutrons blast into these protons? What's going to happen? Well, the next step that's going to happen is these neutrons will then stand still. If they hit these protons, then the protons can move around. But since they're connected in these molecules, if they don't necessarily get debonded, they're basically just going to be turned into heat. And so these neutrons are blasting these protons. The protons are going to move about. But since it's already attached to these hydrocarbons, it's going to stick around better. So these neutrons are are more likely to get slowed down because the masses are the same. This concept I thought was the neatest thing ever. From basic bouncing balls, this was a very practical thing used in physics to protect against damaging radiation, neutrons specifically. This to me was incredible. what you could do with some simple equations. I know we didn't necessarily go through them, but look, this is just a quick page of some equations that you could do with basic simple algebra. It's not crazy difficult, and it's just maybe understanding what this stuff means is where the practice comes into play. You could learn this. This isn't something that's restricted to just physicists that they know this stuff. You learned algebra. Maybe you didn't feel like you were great at it, but with a little bit of effort and some work, we could learn tackle this stuff together. Don't hesitate to stop your learning just because maybe you had a bad teacher. Keep thinking, keep asking questions. You might have examples of this in your life that you've applied to other aspects of your life. You have a story that, hey, someone treated me bad and did this. I didn't like it, so now I do this in response. Physicists do that with their problems too. Hey, they have stories. Somebody's story was, hey, bouncing balls, they collide. If they're the same mass, they stand still. You could apply this to billiard balls. That might be more relevant to you. If you're a radiation or nuclear physicist, this might be more relevant to you, right? If you play football, colliding will be more important to you, right? So you want to know the mass differences. This stuff could be applied in a lot of different ways. It's not just restricted to what we think, right? This is known as a model. It's a way of just thinking of how the world works. And with these approximations, you could apply them to a lot of different things. I don't think you should limit yourself to any little thing just because someone says, "Oh, this is only useful for this." Did you think colliding balls could be useful for something like this? We've already named off many things. So dodgeball, a punch. So for fighting, we said radiation, right? Neutrons getting blasted out. Um, we already said football. You can do. You said billiard balls. There's a lot of different things. The another thing though is these are completely elastic collisions. They might not apply to every situation, but you could tweak some of these equations and then apply it to say a car crash, right? There's things you can do with this. Apply it to space. Apply it to planets. Whatever you want to do. The it's you're only limited by your imagination. So keep asking questions, and hopefully we could go on this journey together. If you have any questions, feel free to just leave something in the chat. I'll respond to it, and hopefully we can go on this journey and keep learning and stay excited together.